Welcome back to Physics. This is Lesson 8. Today we are going to begin a new chapter, Chapter 2, which is representing motion. Now, in the first chapter, we learned a lot of different aspects of physics, measuring things that are basic for future knowledge. Today, what we're going to look at is kind of a foundation for many other aspects of physics. Most of physics deals with something that is in motion. So, my first question to you today would be, what exactly is motion? How would you define motion? Well, there are all kinds of different motions that we can make. For instance, if you are sitting down somewhere, let's say in a restaurant, and you look around the restaurant and you see people at different tables, you may see a waiter over near maybe the cash register. And then you look down at your menu and you look at some of the options on the menu. And when you look back up, you look over at the cash register and the waiter is no longer there. So you look around the room and you see that the waiter has moved to a table and is now taking an order. Well, how do you know that the individual moved? All of our perception of movement is really based off of things that we believe are not moving. Now, in the grand scheme of things, pretty much everything is moving. We have the Earth that's spinning on its axis. We have the Earth that's going around the sun. We have the sun that's orbiting the center of our galaxy. Perhaps our galaxy is also rotating around some other central point in our universe. So there's movement, actually hundreds of miles per hour of movement, and objects that we would consider just stationary. Take, for instance, this board here. It is attached to the wall. We would consider it stationary. However, in reality, it is moving hundreds of miles an hour based on my present location, just if you consider the rotation of the Earth, not even its rotation around the sun, just its spin on its axis. So how do we know when things move? Well, if you take a look at your screen right now, kind of get an idea of where different objects are. And then in a moment, I'm going to have you close your eyes for just a couple of seconds and then open them up again and look at your screen to see if anything has changed. So right now, take a look at your screen. Where is everything located? Now close your eyes and now open them. Did anything move? If you are even remotely aware of what was going on, you will have noticed that I moved from roughly right here on your screen to where I presently am on your screen. But how did you know that? How did your mind perceive that? It perceived it based off of the background that you see, the board that we are assuming is stationary. Many of you have been in a car, perhaps you drive, you've been at a stoplight, and you have your foot on the brake, you're waiting for the light to turn green, and you're kind of looking around, and maybe you're looking even forward, but out of your peripheral vision, it appears as though the car beside you is moving. And your thought might be, is that car moving forward, or am I rolling backward? Particularly if you have a standard transmission, to where perhaps you're in neutral, you might be a little bit on a hill, and your immediate reaction is probably to press on your brake a little bit more. Because if you are indeed rolling backward, you don't want to roll into the person behind you. And so you push on your brake. And then at that moment you realize, okay, nothing changed for me, but the car beside me therefore must be moving forward gradually. But how do we know? We have to perceive it based on our surroundings. If we're looking at a moving vehicle, if we're reading a book, well, we may not even perceive that the vehicle is in motion because we are looking at our book. However, if our car is driving through an area that has trees and the sun is on the other side of those trees to where sunlight gets through a portion of the tree, but not all the tree. You may be reading and you see all these things that are going by, the leaves and the trees and the shadows that they produce on your book. You know that something is moving. If you've fallen asleep in a vehicle, hopefully not driving at the time, but if you've fallen asleep in a vehicle, when you wake up, you may not even know if you're moving or not unless you look out the window. Are things that are stationary, according to our thought process, do they appear to be moving? If they are moving, then that means I am moving, because that object has to be stationary. It's a tree, it's planted in the ground, it's not going anywhere. So I must be the one that's moving. But there are all kinds of motion that are possible. We can have straight motion, such as a 100-meter sprint. We look at track and field and some of those events, and they run in a straight line. But some events are too long to run in a straight line, and so they go around the track. You have a 400-meter, you're moving around a portion of the track as the sprinter is running. So he's not going in a straight line, he is turning. If I had an object that I was spinning, such as a top or a coin, if we were on something like in the background here where it kind of looks like a roller coaster, it's not. It's actually from the 2008 Olympics. Those are the Olympic rings that this gentleman is running in front of. But if we're on a roller coaster, we might be going around and around in kind of a vortex type of loop or shape. So we're not going in a straight line, we're turning. So there are all kinds of motion. What we're going to do at the beginning of this chapter is just simplify things down by looking at the most simplistic form of motion, and that is a straight line motion. And once we get a handle on how we can perceive motion and how we deal with it in physics, then we'll start expanding into things that are rotating and things that are turning, expanding our abilities in the physics realm. So there are all kinds of motion, as I mentioned earlier. But what is motion? Motion is simply the perception that something is changing location. So it's the change in location during a time interval. Now, if I ran this again, where I had you close your eyes right now and then open them a second later, if you did that, you notice that I did not change positions. My hands may have moved from one scene to the next, but I did not move physically from one location to another location. How did you perceive that? Well, you were given a gap of time, roughly a second, but there was no change in my location. Therefore, we would perceive that there is no motion, no movement during that time. So that brings us to the concept of motion diagrams. Motion diagrams are a simplistic way of us representing motion. Now we're going to start off a little bit on the more complicated side, and then we'll do what we actually do in physics. So as I mentioned earlier, an object moves in relationship to its location. So up here on my screen, I have this nice looking gentleman right here. And he is in the top left corner of the screen. However, is he moving? Right now, that picture is not moving. It's stationary in relationship to everything that is surrounding it. However, it could move. For instance, now it is in motion. It is moving. It moved from the top left of your screen to the bottom right of your screen. So that means there was motion, there was movement, because it changed locations based on its surroundings during a time interval of a couple of seconds. It moved from up here down to the corner. A series of pictures of a moving object overlaid on the same background is what we call a motion diagram. We use motion diagrams quite a bit. Now, we simplify it down, but we're going to just take a look at motion diagrams. So initially, I had a picture up here, and then the final location is down here. That would be a motion diagram. a pictorial representation of a before and after. Now, if we're taking a picture of perhaps somebody running in a race, like a 100-meter dash, if you can imagine taking a picture every second. And so if we have the whole view of the whole 100-meter run, and we have a camera maybe in the center, and the gun goes off and it takes a picture as the gun goes off. And then it takes a picture every second in between shots. Well, if you have someone who's a very fast runner, a sprinter, such as in the Olympics, they usually run the 100-meter dash in, 9 seconds or so. So the first second, or time 0 actually, would be at the starting line. So the gun goes off, they're still in their crouch position, they're just now pushing off. 1 second later, they're probably about 8 or 9 meters into their run. 2 seconds into their run, they're probably more along the 20-meter mark. A third second, they're probably closer to the 31, 32-meter mark. And so we take these pictures until we get to the very end where they've crossed the finish line. And maybe it's taken them 9.5 seconds in order to run that 100 meters. So each individual picture gives us a representation of where they are in their run based on the surroundings, based on the background, based on things that are not moving. Now, if we had the background move, it would appear as though the individual is moving. They do this often in movies where they have the background move and maybe the people are just walking in place. But yet, because the background itself is moving, it appears as though the individual themselves is walking down a street or whatever. So this is a motion diagram. If we were to overlay those 10 pictures or whatever in our 100-meter dash on top of each other, we would have a motion diagram because we see the location at each time interval. And normally we try to make those time intervals equal amounts. So every second or every 10th of a second or every 20th of a second. Usually you don't say, well, I'm going to take the first picture at 1 second and the second picture at 1.5 and the third picture at 3 seconds and the fourth picture at 5 seconds. We try to keep it in the equal intervals as much as possible. It's not always possible, but we try. Sometimes we do it based on markings, so when they cross a certain point, a picture is taken and a timestamp is given to that. So it may be equal increments on the picture, on the motion diagram, but it may not be equal time intervals, and that's usually noted on the motion diagram as well. So that brings us to a simpler rendition of a motion diagram, and that's called the particle model. I'm going to demonstrate the particle model. Let's say my starting point is right here on the screen, right where that white dot is, and I start walking. And every step I take, I'm going to put another dot on my screen. So as I walk across, my shoulder kind of ran into it there, you can see a particle model of my motion. Now, normally I would do it, rather than every step, I would do it every second or a certain amount of time that passes by. But for the sake of showing you what it does, this is what it would look like. So we have different particle models. And those particle models represent the location of the individual or of the object at each time interval. When we do this, we want to choose a certain point on the object, preferably a point on the object that is not going to change in relationship to the rest of the object. So let me give some examples, for instance. Let's just say we go back to our sprinter. He's running in a race, the 100-meter dash, okay? And as he's running, we don't normally run with our arms stiff, okay? We run and our arms are moving back and forth. Well, if I pick a point on, say, for instance, the hand as my point of reference when I do my particle model, as I'm running right now, my hand is kind of behind me. So my particle would be right at the edge of your screen. And then a second later, Okay, now it's all the way over here on this side of your screen. But as I continue to run, my hand goes backward, and the next second, it may look as though I didn't move at all because I'm picking a point that in relationship to the rest of my body is also moving. So what we want to do is we want to try to pick a point that is on the object that is pretty much stationary as the object itself. So if we're talking about a human, the leg, not a good idea. The arms, not a good idea. So what points on a human being that is running would you choose in order to get a true representation of the individual running? If you said the head, that's a fairly decent guess. Some people do bob their head a little bit, so you might get a little bit of going back and forth, but it's going to be fairly minimal. We're talking about, a couple of inches, as opposed to the hand, which could be several feet difference. The chest, like where the heart is, that would be a good point of reference because as you're running, the chest is pretty much going in a straight line. It's not going up and down. It's not going, forward and backward during the race. The hip bone, that would also work. If you're running, that's going to go in a fairly straight manner. Bad places, again, would be the arms, the legs. The head would be okay, although probably not the best, although it is likely one of the easiest things to look because you can just look at the ear. As long as they're not turning their head back and forth, the ear is a good point of reference. Whereas the chest, it's like, well, what part of the chest? You'd have to choose a point that is going to be fairly consistent. If you wanted to do like the neck, the center of the neck, that would be a good idea as well. The hip bone is generally a pretty good concept with running. If we were looking at a bird, the tip of the wing, not a good point of reference because those wings are going up and down. And so you're not getting a true representation of what the motion of the entire bird is by choosing the tip of the wings. So just be careful as you look at what point of reference you want to make. We use a lot of particle models when we do motion diagrams because they're easy. You just put a dot on there and you're done. And so you're going to put dots on your paper representing how fast the object is moving or is not moving. So let's take a look at our first problem here. It says use the particle model to draw a motion diagram for a bike rider that is riding at a constant pace. So I'll give you a moment. What would you do using a particle model where somebody is riding a bike at a constant pace? If you have your particle model, it looks something like this, where you have a dot here, a dot here, a dot here, a dot here, a dot here. And all of these distances between those dots are roughly the same, then you are correct. You want them to be roughly the same distance apart because that indicates that somebody is going at a constant speed. Now, let's take a look at the bike rider themselves. As you can see, I am a fabulous artist. Okay, so we've got to get this guy some arms here. Okay, so he's holding on the handlebars. What would be some good points to choose on the bike or the rider that would give us a good motion diagram? I'll give you a moment to think about that. Okay, so let's pick some good points. If you said the head, like maybe the eyeball or something like that, that's probably a good point of reference. Now, I realize that some people are sometimes they're going to crouch down, sometimes they're going to sit up, but likely if they're traveling at a constant speed, they're likely also staying in a constant position as well. If they're slowing down, they might be sitting up, whereas if they're trying to really go fast, they might crouch down to decrease the wind resistance. But if they're traveling at a constant speed, that means they're probably just pedaling along at a constant rate, and they're not really worried about going fast or going too slow. So if you pick the eyeball in that situation, that's probably a good thing. You could pick the hip bone. That's not going to matter even if they crouch down or they're sitting up. That hip bone is probably going to be in the same location. You could also pick a point on the bike, such as one of the axles. All right? You would not want to choose a point along the wheel, the outside of the wheel, because obviously it is going up and down and it's turning, it's going kind of forward and backward in relationship to what the actual rider is doing. So that wouldn't be a good point. You could pick like the seat. You could pick the center of the pedal axle. Really a lot, pretty much any point along the bike other than the chain or the wheel itself would be a good point of reference. You just want to be able to choose one particular point as it's going along so that you have a good point of reference. So there are some good points and there are some not so good points in this particular situation. So tomorrow when we come back for the next lesson, we're going to extend our ideas on motion and kind of expound upon what we've learned, which of course was dealing with motion diagrams, particularly the particle model. It's much faster than doing regular motion diagrams because regular motion diagram you have to redraw the figure each time, whereas we're just going to use a dot to represent the location. When you represent a location, make sure that you are choosing a point on the object that is not moving in relationship to the rest of the object itself to give us a truer representation of the actual motion.